So let's talk some more about the idea of the linear attenuation coefficient. So this is where we are sort of considering or thinking about, say, X-raying through a substance. Let's say this is muscle, and this here is bone. First of all, the thing you need to know is that that idea of intensity I0 is, we're talking about a collimated parallel beam. Now normally, if I get another piece of paper, if I have something emitting light through a gap like this, so the light's coming here, or in this case X-rays, what happens is it spreads. If I take that from like a light bulb, it spreads in all directions, like this. So that means that the intensity when you're further away here is going to be less than it is here. So what we do when we collimate the beam and make it go straight like this, we're making it spread as little as possible. So that intensity is only reducing because of what it is passing through and how it's being absorbed. So we're getting that idea that the value of energy that it has is getting less and less and less. So attenuation is that reduction in power, reduction in intensity, or reduction in energy, and you can say any of those things when you're talking about your understanding of attenuation. Okay, so if first of all, if I'm asked to explain what the linear attenuation coefficient is, I have to say first of all, in a parallel beam of X-rays, that would be 1 mark already, just for saying that it's in a parallel beam. I can say it is the value mu in the equation I equals I0 e to the minus mu x. That would be 2 marks. It's fairly unsatisfactory in a way, isn't it? And then we say that where I is the intensity at that distance, x. So what do I mean by that? Well, if I'm passing through bone, for example, it would be that distance x, and it's in centimetres usually, especially in our exam questions. It's in centimetres, but you must take a close look at the units. So that's the distance x. It's saying what is the intensity here. Okay, so that's what we mean by I. At that distance x, through the material, with I0 as the original intensity. In other words, right here, that's where it's I0, then it starts passing through. So in air we say that attenuation is fairly anything, it's negligible really, and then when it gets here, it starts going down. Now on our PowerPoint that I was talking through earlier on in this video, all the values are in per meter, but in the questions they're usually, the value of mu is measured in centimetres to the -1, so it's the amount it goes down per centimetre. So the amount the intensity goes down per centimetre. Okay, but when it comes to answering that question, we can, of what's our understanding of linear attenuation coefficient. That linear part's really important because that's implying it's that parallel beam in a line. If we were allowing that column to spread, it would be losing its intensity as it goes further and that can't happen. It has to be collimated. And then I can just quote the equation. Okay, so yeah, that's what we're talking about here. So we're back to our drawing here. We start with that collimated beam, and then I'm just going to sort of model it slightly. It's going to sort of reduce as it goes through here in its intensity. Not get thinner, it just gets less. Its value is less, and then it will get less and less and less in the bone. And it could be absorbed altogether, and that's why it ends up being white on the image, whereas everywhere else is dark.